Alright, good evening and welcome everybody to N Simplex Pachinko. I am your host here, Obi-Wan Pez, and we are looking to get into some discussions about Calc 2 tonight, and probably also a little bit into, I believe it was Matthew brought up a couple weeks ago, the Cistercian Order Notation, or rather, I brought up that there was this cool kind of way of writing numbers. Um, um, I wanted to talk about the Cistercian Order Notation, which is kind of like a cool little aside. Unfortunately, you can't do a whole lot of math with it, but it does look kind of nice. And the numbers themselves were used mostly for non-mathematical purposes, so stuff like writing dates or page numbers or various other things like that. This was covered in an episode of Numberphile by Alex Bellos, or with Alex Bellos. Something about Europe's lost number system or something like that. I highly encourage you to watch because it is a brilliant segment. And Brady Heron, the guy who runs Numberphile, is a very nice documentarian. I like his work, and I will support that channel for for the foreseeable future. Um, all right, so right now, and then later tonight we can do whatever. So if anybody has any requests, feel free to ask, uh, and we'll get into some of that cool stuff. So the last couple of weeks we've been talking about various items in Calc 2, and most recently we were starting to talk about numerical integration. So when we start having problems trying to calculate individual integrals, and we're not actually able to solve them analytically, sometimes there are better ways of trying to figure out how these are better ways of trying to figure out what the values of the integrals will be. So, one of the problems that we came across was when you have something like, an integral that is literally impossible to try and solve, such as e to the x squared dx, like this, and normally we'd be looking at trying to figure out, like, what is the value of the definite integral between 0 and 1 of this particular function. Solar Reaver, sorry, I blanked on. Hi, how are you? I know we talked a little bit before, but still. Hi, good to see you. And I guess real quick, is the mic balance okay, or is it really kind of quiet still? Because I have been having problems with this microphone. Allegedly, a lot of people are having problems with... Okay. Allegedly, a lot of people are having problems with microphones lately, with them being 100% maxed out on every single layer, and it's still too quiet on the stream or on the video. So I just wanted to... Okay. Thank you. So in doing or in trying to do an integral like this, we've got a problem here. You can't actually take the integral. So one of the things to do is numerical integrate. Okay. Numerical integration, which is at least finding a decent approximation for this particular integral. So if we're looking at the function e to the x squared dx, and we're looking over the interval from 0 to 1, several ways that you can do this. One is that you can fall back on the original definition of what is an integral. Well, an integral is basically, hang on, yeah. All right, we've got something like this, Now, granted, this would be 0 and, like, this would be 1, basically. This is definitely not to scale. This would zip off to infinity extremely quickly. But the idea here would be, again, we still want to get what is the area under the curve here. So the definition of integral can come into play in that we can look at this as a series of rectangles that are all built off of each other. And we're looking at Riemann sums. Now this is, again, something that we've looked at in like Calc 1, so generally speaking, you're not going to be sticking with this 100% in Calc 2, but maybe we'll go with a really thin one. See how this goes. Alright, so we're going to be doing Riemann sums on this. But again, this is a Calc 1 method, so it's not super sophisticated. It still gets the job done, at least, you know, in getting an approximation. Generally speaking, in Calc 2, what you'd want to be starting to look at is how to do this in a programming language. So use Python or MATLAB or, you know, Perl or whatever you got. Perl, lol. Or whatever you got. And you're probably going to figure out how to do basic Riemann sums and then be able to figure out better approximations using maybe a little bit higher level mathematics, but fewer problems in general. So Riemann sums are a form of numerical integration. Now, the problem with this, for the most part, or one of the major problems with this, is that these are really quite inaccurate. So if you were to zoom in on this, you notice that this is missing quite a lot of space up in here for using rectangles. So one of the ways to fix this is to, instead of rectangles, you could actually start using... This is really big because I'm so zoomed in. But you could start using trapezoids that connect these particular points with straight lines. And trapezoids are much better in terms of trying to figure out what the area under this curve is, due to the fact that we draw a straight line from any one point to any other point here, which will cause us to have, again, better approximations. Not 100%, but pretty decent. So the trapezoid rule is a nice, easy fix for Riemann sums to be able to figure out what the area of the curve is. Again, it is a better approximation. It is not a perfect approximation. If, however, your delta x begins shrinking to 0 and we start getting a limit as the delta x goes to 0, then that's going to be equivalent, right? It is literally the same as the... they will always... yeah, the Riemann sums and the trapezoid rules and anything else that we figure out, if delta x goes to 0 and we take that limit, it will always literally be the same value. Right, the only way in which these are different is that on a larger scale, when delta x is not approaching 0, we start seeing a problem because, again, these are finitely large. All right. Alright, so then one of the other method, well, let's write this one out. Come on now. Alright, let's go back to normal. That's not possible. Alright, so when we start looking at this and we start thinking about trapezoid rule, alright, in order to figure out the area of any one of these trapezoids, we're going to be taking, let's see, let's draw in one of these. Looks like that. Close enough. So in order to do this, we'll look at this and say, okay, what we want then is, this is going to be the average of the two bases that we have. And these bases are, well, we'll figure that out in a second. But b1 plus b2 multiplied by our height. Now the height of the trapezoid in this particular case is actually its width. So this is actually a real easy thing to figure out, right? What's the width of each of these individual trapezoids? And they are delta x. So whatever delta x actually is. That's what we're going to use. And in theory, we could have delta x's that are of varying sizes. I did talk about this last time when we were talking about like sums and using delta x for our basically like Riemann sums. You could use a variable delta x sub I to represent any number of potentially differing sizes in heights. Now, in some cases, like on this nice kind of smooth curve here, it's probably not going to matter all that much. Your delta x being all the same all the way across is probably going to get you a decent enough approximation. However, if you have any sharp turns like this on it, you know, having a trapezoid like this is really going to kind of mess you up, because now you've got this internal part which has like a concave down section, and you're drawing a straight line, and it's going to chop off a bunch. So it's not a big deal, but you know, if you're looking at this, you might want to say, for instance, around any of these particular steep areas, so that's when f prime at x is much bigger than 0. And actually this should be like absolute value, because it doesn't matter whether it's positive or negative. But if you take the value of your derivative and it's much bigger than 0, you probably want to have you want to make your delta x be fairly small. And when we are around flatter areas, meaning that the absolute value of, you know what, that doesn't even matter. f prime at x is approximately 0. So really close. Delta x can be larger, so you just make something that goes much wider across and then draw your straight line. It's going to get you much closer approximation. Right, so the effort that is required when your delta x, nope. The effort that is required when your f prime is close to 0 is much less than the effort required when your delta x is, no, when your f prime of x is much larger. Oh man. Alright. Alright, what about b1 and b2? Well, if we're doing like Riemann sum type stuff, our initial one is going to be this left part here. Our base is going to just be the function value at this particular point. So this is going to be like f at x sub I. It depends on how you want to number this or how you want to index them. If you're going to start from 0 and go up to n minus 1, then we're going to start with just I. If you're going to start with 1 being here and go up to n being here, then we're going to have to make this I minus 1. So it kind of depends on how you're doing this, but it's not a big deal. Either way, these are sequential, or they are adjacent to each other. So we're going to end up taking the average of these two particular function values and then multiplying by our height of the trapezoid, which is again the horizontal portion all the way over there. Okay, horizontal portion here. So then if we want to find the area of all of it, what we're going to get is then it's actually not going to be in an equality here. This is going to be approximately equal to the sum of all of these individual areas. So I is going to go from 1 to n. It's just kind of my habit. It'll be 1/2 times the function at x sub I minus 1 plus f at x sub I times delta x sub I, or we can approximate it using the sum as I goes from 0 to n minus 1. 1/2 times f of x sub I plus f of x sub I plus 1 times delta x sub I. It doesn't really matter, again, how you're going to number this. It really just matters like what your notation is compared to what you have on your picture. So delta x sub I, if we're saying like delta x sub 0 is going to be the one from x sub 0, then that's fine, we can do that. Alright, so this is really what we're going for with finding the area under the curve using a trapezoid rule. And again, what you'd have for... I need to stop using red. Apologies if anyone is colorblind. I keep using all sorts of colors anyway. Alright, so... if we want the exact actual area under the curve, then all we have to do is just the same as the Riemann sums. We take the area under this particular curve is going to be equal to the limit as n goes to infinity, delta x goes to 0, or n goes to infinity, however you want to say this. You can just pick one. It's going to be the limit as we go from I, goes from 1 to n of 1/2, parentheses, f of x sub I minus 1, plus f of x sub I times delta x sub I. So in this particular case up here, we might want to say like, well, let's do numerical integration on, delta x being, let's say 0.1. I'm not going to do it by hand because it's going to take a little while. It's not terrible. It's not terrible. Oh, actually, right, there's something else we need to do here. So when we do this, this can all be written out in a long form. And I'm not going to write the whole thing, but at least a few terms here to get the point across. So if we start at the beginning, this is going to be, if I is 1, then we end up with, well, this 1/2 is going to be factored out from all of it, because it's all going to be the same value. Delta x, I've said, we're going to keep it constant for a lot of this stuff that we're doing, so delta x sub I is going to be constant throughout all the values. So actually we can write this as 1/2 times delta x. And say that this will be approximate. So 1/2 delta x times, from the first group we have I equals 1 is going to be f of x sub 1 minus 1 is 0. So that's f at x 0 plus f at x 1. Then we have the next term. So I equals 2 is going to get us f of x sub 2 minus 1 is 1. So this is going to be f of x1 again. I figured y'all didn't need that in your face. Alright, plus f of x sub I, which again is x sub 2 at this point. Okay, and then the next term after that is when I is equal to 3. So then what happens? Well, this is going to be f of x sub 2 again, plus f of x sub 3, plus the next term over is going to have f of x sub 3 plus f of x sub 4 plus, and then it's going to just keep continuing on until we get all the way out to f of x sub n minus 1 plus f of x sub n. So here's the thing, right? We notice here that we're going to have a bunch of these terms are all going to be paired up. And that also includes f of x sub n minus 1, which is going to be paired up with the previous term here, just like f of x sub 4 is paired up with the next term that I didn't actually write. F of x sub n is the only one beyond the first term, f of x sub 0. Okay, let's just go with that. F of x sub 0 and f of x sub n are the only two terms which have one of them. Every other one comes in a pair, so there are going to be 2 of all the rest of the terms, which means that this area can be approximated. Again, area of this curvy thing can be approximated by 1/2 delta x times f of x sub 0 plus 2, and then you could put this in parentheses, or yeah, you could put this in parentheses if you feel like it, or just do it like I'm going to do it here. Twice f of x sub 1 plus twice f of x sub 2 plus twice f of x sub 3 plus dot 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 out to twice f of x sub n minus 1 plus 1 f of x sub n. So that's how you do it with trapezoids. And now we can get this nice little, yep. Now we can get this nice little formula here, which allows us to just plug in numbers. I mean, I could do it on my TI calculator in just the list area. I don't have to make like this big complicated thing. I believe... I don't remember how to make a long list without manually doing it, so that's kind of annoying. But there is a way to do it. You can make a list that's like 100 elements. There we go. 100 elements long. So in your calculator, those of you who have TIs, everybody else, I'm sorry. So in your TI calculator, you can create a list. So like L1 is going to be equal to, and then you do this as like 0. 0.1, 0.2, 0.3, etc., all the way out to 0.9, 1. Now this one's only 10 units, or 10 elements long, so that's not too bad. But if you did something like L1 is equal to 0.01, 0.02, and then kept going like that until we get 0.98, 0.991. I'm sorry. No, you know, Casio is pretty good. I just have never actually had the chance to like sit down and use one. So, like, I have no idea how to do anything on it. My students are like, "Oh yeah, it's nice and easy." I'm like, "Great. Have fun." And I mean, that's my fault. I need to get better. But at the same time, like, nobody's... Yeah, Casio's not going to offer me a sponsorship now. Oh. Yeah. I've also got my TI... God, where is that? Got my 86. Yeah. Here's the one for the TI 83 Plus. Yeah, TI 83 Plus. Not very big. Here's the one for my TI 86. Roughly the same book size, however, it's like twice as thick. So anyway, yeah, the TI 86 I really like personally, and they discontinued it, so I'm slightly unhappy that they did that, but whatever. Okay, it wasn't selling as well. I guess they made actually good marketing decisions. But anyway, yeah, my 86 is... Well, the entire point of the 86 is really just that it is an engineering calculator. So it is for engineers. It is for people who are going to be doing stuff like this crazy, you know, numerical integration stuff, as well as differential equations and, you know, higher level math. So I ended up getting my TI-86, my last TI-86, for about $40 on eBay. I got a TI-89, probably silver or something like that, and I still don't know how to use that one properly either, for like $50. So like all these ones that are now discontinued, they're really old calculators comparatively, And yeah, I don't pay much for my calculators. Okay, so if we're going to be doing creating a list, what you then want to do is take L2 and set that equal to basically y1 of L1. So in a variables menu, you can select like your y expression is then just going to have all this stuff plugged in as if it were just function notation. And so it reads all of the elements of L1, whichever list you have, and then fills L2 with taking those numbers, plugging them into the function. Calculators and computers excel at this. That's all they do. Like, that is their main purpose, is to execute simple calculations like this. So I would not want to do any of this stuff by hand like they did, 100 years ago. That's insane. Don't do that to yourself. Let the calculator do the heavy lifting for any of this stuff. And this is also why you should, usually speaking, typically, learn a programming language of some kind so you can at least be able to figure out some of this stuff. So I'm still trying to work out Python. It's going okay. I haven't touched it in a couple of months. I definitely need to get back on it. I'm also trying to do some of my research in Python. It's much harder to do 5, 6, 7-dimensional research when you're, used to doing 2 maybe. But hey, whatever works. So anyway, yeah, if you take L2 to be equal to y1 of L1 as function notation, then all you really need to do is then look at this and say, okay, what I'm going to do then is I'm going to take the sum of all of the things that are in my list, and then you could probably do this. So like the sum of L2 and multiply it by 2, but then we have to get rid of the first and last. So then we have to subtract off L2 element 1 and L2 element n plus 1. So whatever that is. If this is 0, no, if this is 1, this is 10 plus 1 is 11. So either 11 or 101, whatever number it is here. So this really is just n plus 1. So subtract off the first and the last elements, and then this is going to be your approximation for it. Oh. Like the stuff moving around isn't jittery anymore? Is that what you meant? So I have also, in the last month, upgraded my... Oh, okay. Wasn't going to be me anyway. All right. Yeah, so I did upgrade my hard drive. I popped in an SSD, and then also I doubled my RAM. So on my end, there should be no problems. Let me just double check here. Yeah, I suspended that. Okay, cool. Yeah, when I say double my RAM, I don't mean like, 100 or whatever gigabytes. Yeah, it was still at 16. I doubled it to 32, and like I don't notice a whole lot of difference most of the time, which is fine. It's just like when I need to change what I'm doing, then it actually matters. And giving the SSD the availability to say like, oh, by the way, you can use this as virtual memory. The computer sometimes doesn't even know what to do with itself. So you're saying I have all this space? I know you're not. You're supposed to max out at like double what you have. So I should be maxing my virtual memory at allegedly 64 gigs with then this 32 hardware. So I don't know. We'll figure something out. Alright, so if we look at the original one, integral from 0 to 1 of e to the x squared dx, then we can we could say, for instance, let delta x be 10, no, sorry, 0.1. So then n has 10, 10 whatever. N equals 10. There are like 10 intervals over which we're working. Then what we're going to do is, again, looking at this area is going to be approximated by, that is 1/2 0.1 times f at 0, oops, not comma, plus twice f at 0.1 plus twice f at 0.2 plus all the way out to plus twice f at 0.9 plus 1 f at 1. Alright, so then that's going to be a 0.05. That's the 89. Oh, well. Really wanted my 86 because I know how to do this. Where did I put it? That's weird. Alright, table. I don't know what I'm doing with this thing. Alright. There you go. Table set. Table start with 0. Delta table is going to be 0.1. And then y equals, yeah, there we go. E to the x squared. That's not what I asked. Okay, there we go. Alright, so then this is going to, I mean, that was obvious. I should have just done that one, but whatever. Plus twice at 1.01 0.00501, etc., plus twice at 1.0408107, more stuff, plus, oops, twice at 1.094174, more stuff, plus twice 1.1735108, plus, this is where it gets a little tedious. Twice at 2.24707, more stuff, plus 1 times, and here we get E, so 2.71828, 1828, 459045, etc. So if we again sum all this up, let's see if I can just sum all of this, because that'd be nice. Not gonna happen, huh? That's too bad. Quit. There's a quit button, I know there is. Just pop out to the home. Close enough. Alright, list sum y1. Oh, stop. No, because that's not a finite list, that's the infinite list. I could just keep going on this. Yeah, no wonder it's going to have a problem with it. It's not going to be nice, is it? Alright, let's see if I can manage to do this. Probably not, but it's fine. Sequence 1, 2, that's not the button. 210. No, okay. Alright, whatever. We'll just pass on the TI-89. So yeah, if you do this in, we can do this in pseudocode in MATLAB, but something like del x equals 0.5, nope, 0.1. Sims x f at x equals e to the parentheses x squared, like that. We don't even need to do that necessarily, but that might be the easiest way. Otherwise, x could be equal to, this is where you build out the actual 0 to 0.1 colon 1. And then like y is equal to e raised to parentheses x dot raised to 2. That should do it. In this case, we could just do what we did up above, where this is a equals 2 times sum of y minus y sub forget if they do zeroth. I think they don't. So it should be y sub 1 minus y sub 11. Something like that. You can't see that. Y sub 1 minus y sub 11. Yeah, I think that'll work. There's also this nice online Octave. Let's see if I can pop that up. Oh yeah, it is here. I already have it. So I'm going to type in the pseudocode like I did here. This is going to be del x equals 0.1. Okay. I don't remember actually typing out. That's weird. All right, cool. 0:0.1 colon 1 gets me all those values, okay? So then y equals exp parentheses, not e raised to. That's going to be important. Alright, so exp of x dot raised to 2. Yep, okay, cool. So then we do a equals twice sum of y minus y sub 1 minus y sub 11. Alright, cool. So this returned a value of 29.343. Let me see. If we had done, let's say, Sims, let's do capital X. It's not a thing. Yes, it is. Okay, cool. F of capital X is equal to exp parentheses capital X squared. Okay, that worked. All right, so then capital Y is equal to, let's try this. So capital Y is equal to F of don't know that this is actually going to work. Yeah, I don't remember the proper code to make this work, but that at least, this at least does work for what I'm trying to do. So if you manage to figure out the proper pseudocode or the proper code in MATLAB for all this using actual function, like embedded functions and all that with the proper notation and everything, then you know you can use that just as easily. However, this returns it as e to the x squared like that. And then again, you have to figure out like how to get this to output the proper values. I want to try it just in case. So capital Y is equal to f of I don't think this is going to work, but let's try the 0 colon 0.1 colon 1 thing. Yeah, no. What are you doing? Yeah. Came out with some weird notation, but it does sort of believe me that that's a thing. All right, so then sum y is equal to okay, and then how do you get approximations? How do I change symbolic displays? Yes, that one. Eval. Format. Maybe. Oh, I lost it. Where'd it go? Yeah, there we go. Okay. 16.531. So something went wrong there. Oh, that's awful. And it's not even like sort of wrong. It's super wrong. What did I do? Oh, yeah, I didn't. That would be the problem. Okay, let's go back. Okay, so we need to do twice sum y minus y1 minus y11, right, like I talked about before. That gets us this. Ah, there's e. E is like stuck in the middle. It's so weird. I don't know why they'd ever want to do that. So eval answer is 29.343. Okay, so now, right, this isn't the area because I also forgot to multiply by 0.05. So, completely forgot. So then we can erase that. And we'll multiply by, it's approximately equal to 1/2 delta x times all that stuff. Okay. So multiply by 0.05. Okay, so we are getting the same thing. Good. This then, the way that I had done this gets us an exact answer, and it puts it in like the proper notational form, so it's a little weird, and you don't necessarily need to do that. I'm just going to stick with this one for now. So it evaluates all the individual values, and that's also a weird thing about MATLAB is that it really requires this right here. I shouldn't say weird. It makes a lot of sense when you understand what MATLAB is trying to do. MATLAB is a matrix laboratory, so you are trying to do all sorts of things with matrices. So when you try to take x and square it, it thinks that you want to take the matrix x and square it. And so in this particular case, we have a matrix that is 1 by 11 with all the individual numbers 0, 0.1, 0.2, 0.3, all the way up to 1. That's a vector. When you try to square a vector or multiply it by itself, you can't do that, right? You look at it, and it does not create anything. You can't multiply a vector by itself. You have to multiply a vector by a vertical vector, or a vertical vector by a horizontal vector. Right? The dimensions need to agree. So when you just multiply a vector by itself, the dimensions don't agree, the inner numbers don't match. And it's really important to understand what would happen if they in fact do match, because you don't necessarily want a square matrix times itself unless that's really what you want. So just be careful with all that stuff. Alright, so 29.343. Alright, so we're going to eval 0.05 times all this stuff. No. Let's try that again. We're going to do... Oh, no. That's not what I meant. We're going to do 0.05 times the evaluation of all that stuff. There we go. Okay, so this gets us an actual value of 1.4672, which makes much more sense when you're looking at an area that is between 0 and 1 and kind of, you know, well, has y values between 1 and 2.7. Obviously, it could not have had an area near 30. So I should have realized that very quickly, right at the beginning. Okay, so 0.05 times all this stuff ends up getting this. Now, if I want to do this with 1,000 terms, I could do that super simply on Octave / MATLAB. Let me actually show you what I'm doing with this. I get kind of nervous when I'm like showing stuff that's on my computer, just because like, but it's okay. I got this one. It's not like anything sketchy at the moment. It's just, well, I don't want to like randomly call out people on the internet. Be like, look at this guy's stuff. Let's see, that's gonna be the second one allegedly. Nope. Alright, so that's the book that I'm using. Let's see, number 1. Yeah, Octave. So this is Octave Online. Yeah, I gotta shrink that down a bit. No, that's okay. Alright. So I'm taking out the top layer of it, but whatever, it's fine. So what I'm doing here is I'm saying that, let's see, I think you can also see my cursor. Yeah, cool. So what I'm doing here is I'm saying that I wanted to evaluate this answer, and it gave me 29.343. This is truncated a lot. So you can actually expand this out further by telling it that I want a certain number of decimal places, and then it'll give it to you. So with MATLAB, I didn't even use the delta x variable at all. I just, yeah, that's terrible. All right. So this matrix 1, 2, 3, 4, I don't even know where I got that from, so I assume that's a previous thing. Okay, so when I wanted a vector that was all numbers from 0 to 1 spaced out by 0.1, that was going to be 0, colon, 0.1, colon, 1 inside of square brackets. And I could have muted this as well. So if I want to, I could say like, okay, x is equal to, do the same thing, but now put a semicolon at the end. And this time I'm going to go 0 to 1, oops, 0 to 1, but in between, I'm going to go, we want 1/1000th. So, I mean, you could literally just type it in as 1/1000th, or you can type it in as 0.001. So either way, that'll work. That popped us back to the bottom. And now it's telling us that this is a 1 by 1001 dimension matrix, X. All right, so then using the pseudocode that I had from the whiteboard, what we would do then is say that y is going to be equal to exponential x dot raised to second power, and then also mute that output. Because again, this is 1,000 things long. I still want to be able to see if I screwed something up here. So now that's going to tell us this is also a 1 by 1001 matrix. Okay, so then A, or capital A that we did before, is going to be equal to, here's where I screwed up before. This is going to be 0.5 times, we got to change del x. So actually, even before I do any of this, del x was going to be 1 over 1,000. And so that's going to tell us it is 1 times 10 to the negative third power. Okay, then technically what I'd want to do is actually not use this, but use it as 0 colon del x colon 1. And now, whatever the size of del x is, it's just going to use it. So in this case, it's 1/1000th. And again, it's going to give us a 1 by 1001 matrix. Now, technically nothing changed. It's just a matter of syntax and like, how do you type this in so that it's the least amount of work for when I change something? All right, so, you know, some other time. Just dismiss that. Anyway, so some other time, if I want to come back and alter this exact same sequence of steps, I can just do that by changing del x to some value and then coming back up through all of the previous commands by hitting the up button. I could go back to something I've done before. And for instance, in this case, right, this was evaluate. This is the wrong one. I'm going to evaluate. This is 0.5 times del x times evaluate twice the sum of y minus y1 minus, and really this should be like the last one. Now, I don't remember how to do this exactly, but I think size of y second dimension tells us it's 11. Oh, yeah, that makes sense. Little y is 1001. Okay, so I want actually that term to change, or I want that term to be subtracted. So I want the first term to be subtracted out, and I also want the size parentheses little y comma 2 to be subtracted out. This is going to be 0.5 times del x times evaluate twice the sum of little y minus little y1 minus little y of the size of y second dimension. Hopefully, this will get us a value that's close to 1.46. It should be a little bit higher. No, lower. It should be slightly lower. Because this function is concave up, right? All of the straight lines are going to be slightly higher than the actual function curve. So this should technically be slightly lower than 1.4672. All right, what do we got? Try must be a string. It didn't complain earlier. That's weird. Okay, so let's just manually change this to y of 1001. No, okay. Huh. What the hell is try? If anybody has any bright ideas, let me know. That is weird. Alright. Let's just check real quick. Alright. I have a whole bunch of bots in channel. Woo! I believe that, maybe, anyway. I don't want to insult anybody. But with a name like Telemans, kind of sounds like. Yeah. Alright, well. Maybe, maybe not. Alright, anyway, yeah, line 14, right. I mean, even line 13 went through, I was just wrong. And it came out with the same numbers. You know what? X and Y, little x and little y might for some reason be like reserved. I don't know. Whoa, that's not what I wanted. All right, let's see if it's reserved for some reason. So capital Y is going to be equal to yeah, I mean, like, del x is that number. And if we just do, like, del x times eval e. 1. There you go. Let's do times equals. Nope. Yeah, so what if we did like, that is interesting. What if we do e times eval e? No, it doesn't like that either. Huh. It'll do that one. Okay, so let's go back up here. And let's do that. It's so weird. It didn't ask to do that earlier. Man. Okay, well anyway, 1.4627. So yeah, it's slightly lower. Yeah, if it might be the other way around, it's possible. but it wants it to be, specifically wants it to be string, so like you put the apostrophes or whatever. Yeah. So it didn't do that earlier though. That's so weird. Why would it allow it here but not down here? Oh my god. Alright. Whatever. That's a clear indication that I should just give up, right? Alright. So let's try this then. Because I think that this is going to work just fine now. Yep. So that's the actual code that you'd want to use for that particular line. That might also have something to do with like you might be right in that it just requires it to okay, so that's the same. Now let's try removing the string tags from it. No? Okay. It's just going to be finicky occasionally. Alright, whatever. So anyway, we got the answer there. So 1.4627, it switches the numbers around compared to our previous one from... That literally does not happen, right? It's not that it's switching the two values, it's just that the better approximation is 27 instead of 72. It happens to work out that way. Right, let's switch back. Whiteboard. So for del x equals 1 times 10 to the negative third, then we get area approximated by 1.4627. And again, this is also like, you just extend the number of decimal places out, and it's fine. Then if we want like an exact value, we can always go to Wolfram Alpha, and it's going to tell us some ugly gamma function, which I still don't understand gamma functions, so yeah, whatever. Or you get the better approximation by saying like, okay, evaluate what this thing actually is, please, Wolfram Alpha, and it will give you something much bigger. So let's switch back for a second because I need to remember where exactly this was. There. All right. All right, so as promised, I need to talk about the Cistercian numbers real quick, but for when Matthew gets back. So the Cistercian Order was a bunch of ascetic monks who lived back in the, 1000s, basically. But at some point or another, they started discovering that their particular number system was not very elegant, and that for instance, Roman numerals that were in use all across Europe were complete trash. And so they were like, well, if we wanted to write, the number 1066, which, Battle of Hastings and all that, English history, this is, M 50,000, 50, 60, 65, 66. So MLXVI ends up being 1066. 1971. There's one that's really awkward, and I can't remember what it is now, but... But to get 1900 is MCM, so 100 before a second thousand. It's pretty awful. 70 is LXX, and 1 is I. So MCMLXXI is 1971. And so the Cistercian Order monks were just like, this is pretty inelegant. I don't like it very much. Let's come up with a completely different number system. And so they began writing, they began writing their numbers on sticks. Some of them are horizontal, and some of them are vertical, depending on who you ask, basically. But the idea here is that you would have simple numbers, which would be able to be written, and this covers all numbers from 0 to 9,999. So 10,000 numbers. To write dates, or as I said at the beginning here, if you write page numbers inside of books, it's real easy to write them using these Cistercian numbers. And again, pretty much anything that is non-mathematical, non-calculation. So again, the page numbers in books, the like decorations or years are very simple to do in this way. So the idea was that you would start with a 1 is just going to be like a dash at the top right. And anytime that you want to write any numbers that have to do with the ones place, this is in decimal notation as the numbers of the time were being developed. Everything was pretty much base 10. Even the Roman numerals were sort of base 10, despite the ugly nature of the various letters that they kept using. So 1 was here. You know what, let's take this one out here. Let's just take that. So this is 1. This is 2. This is 3. 5, 6, 7, 8, 9. Okay. 4, 5, 6, 7, 8, 9. Alright, so 4 was from 2 and go up like that. 5 was a combination of 4 and 1 in that it is both this and that. 6 is one that's completely separated. 7 is a 1 and 6. 8 is a 2 and 6. And 9 is a 6, a 1, and a 2. Or 6 and 3 makes 9. Although, oddly enough, it does not take the 3 and 6 and do that. It's, for some reason, they decided the little flag was just easier to see. This very well could have reasons for why this is the case. I just don't have any answers. So the ones place was all at the top right-hand corner. And then the tens place was at the top left-hand corner. So you'd have your 1s, your 2s, your 3s doing all this. So this is 10. If we wanted 20, that would be here, and so on and so forth, right? We could do 60, etc. And the hundreds were placed at the bottom right. So there's 100. 200 would be here. Again, going out to like 700 would be a hook from the bottom. That's fair. Part of the problem is I wasn't actually looking at my monitor, or I wasn't looking at the Twitch monitor. I was looking at this monitor, just watching my whiteboard. It's fine. All right, so we got 100, 200, 700 looking like this, and then thousands we're at the bottom left-hand corner, so 1,000. Right. 1 and 4 makes 5,000. And flag at the bottom makes 9,000. So then if you wanted to do like 9,638, all you'd have to do is remember what all of these mean. So thousands is going to be at the bottom left is 9,000. Hundreds is at the bottom right is 600 is going to be a line there. 30 is tens is the left side up top is going to be 3 arrow. And 8 is going to be a 2 and a 6. Yeah. So 9638 looks like this. 7,380. What? Let's do numbers I haven't done before. 7,500 and what numbers haven't I used? 20. 1, 2, 3, 4. Alright, so 7,524 would be similarly 7 on the bottom left for thousands. 500 would be the bottom right, and 5 is the sort of foot slash flag going that way. 20 is the top left, 2 is down here, and 4 is at the top right, and it goes that way. So like I said, very interesting in terms of like just being able to use the numbers, but just like Roman numerals, it's practically impossible to actually come up with a system of like adding, subtracting, multiplying, dividing using these particular numbers. It just isn't really convenient in any way, shape, or form. There's no easy way to go to carry, for instance, hundreds into thousands. So here we're adding 600 and 500. Well, hundreds are in the bottom right, so I've got a 600 here and a 500 here. How would we be able to combine these two things, right? It doesn't really fit. And then the other problem is that this only goes up to 9,999. If you try to get a number 10,000 or any higher, it's not going to work at all. So you can't come up with anything else. But on the other hand, these are also ornamental, right? They look pretty. They look very interesting. And if you flipped pages in a book, you'd start noticing that, like, I mean, these are monks, so of course it's probably mostly going to be the Bible and like naturalist type books, being able to figure out like what's going on in real life. So like the physics books of the time would have been something that monks were really interested in, like math books of the time. So those would potentially have high numbers of pages. Probably not in the multiple thousands, but, you know, high. It's still 1,000 times easier, rather than trying to add these, to translate these numbers over onto an abacus, combine them in the way that you need to, and then translate them back. And again, it only goes up to 10,000. So, not going to help. Allegedly, I read something on Wikipedia, like, you know, when I was just pulling up the image for this, that they may have also tagged some of these with like allegedly, like, you have a line that you're going to start your number on, but like subscripting this would mean like basically all of these are times 1,000 times 1,000. So whatever you're doing, this is now going to be millions. But then you don't have like the right number of decimal places, because millions has 6 numbers after it, and this only works with 4 at a time. So it'd be like, you know, your millions number and then the next 3. And then you'd have to have another one for the last 3 numbers, which potentially, I guess, if you went like this, that would tell you that this is now going to be the thousands. And then you just leave off the actual thousands and then start with your hundreds, tens, and ones to make sure that you've got, you know, I don't even know. This is this is getting far afield, and I was not there, so whatever. But yeah, allegedly there was also some of the people were also using like sideways versions of this to be able to write it this way instead. So like this would be yeah, whatever. Like that. Which then allegedly this makes no, I don't like this at all. 1, 2, 3, 4, 5, 6. Okay. 7, 7, 9. 7, 8. What? Those are not consistent. Oh, that's awful. I can't understand this. Okay. Vertical stave had only been used in northern France in the 14th and 15th centuries, so much later on. Horizontal stave was actually more common. Yeah, I know Octave is gonna... Anyway. If you're offline for a certain amount of time, Octave decides that you're done and closes the connection, which, you know, to be fair, makes perfect sense. 4, 1, 9, 9. 7, 1. That's gotta be 7, 0. 9, 7, 8, 4. Ew. Yeah, they're not particularly consistent. 4,484. 715. Okay. So allegedly, this should be then 8. Yeah. 8, Then here is 3. Nope, it's not a 3. That's a 4. 4, 9. So this should be 8, 4, 4, 9 here. Yeah. Okay. According to the source I'm using here. Again, Wikipedia, not super great, but whatever. It fits most of the time. And again, good starting place to get other sources from. So yeah, 8, 4, 4, 9. You read this kind of from right to left and in sort of an N shape, backwards N. So again, I'm going to recommend... So he did this one with Brady on the lost number system, which is the Cistercian notation, which, again, decorative, very nice looking, not very useful, especially in terms of actually doing mathematics. So this is one of the things that I like. Well, this is one of the things that I like doing with mathematics, is being able to show like all of the various all the various crazy stuff that has been done in the past, and looking at mathematical history through this lens to be able to say, this is kind of an interesting thing. Let's explore what kind of let's explore what these people were thinking at that time, and then try to understand like where they're coming from, what were their limitations, not just as mathematicians, but like also as a society. What were these people's limitations because they did not advance their number system? In terms of the Cistercian order, they didn't care because they weren't mathematicians, they were monks. So most of their life was spent in devotion rather than doing academic work, although many of them still did. Alex also goes through an interesting section and talks about how the Cistercians also usually invoked vows of silence, and so during a lot of their life they would be absolutely silent, and they had to develop a way of communication that did not use vocal communication. And he said that there was basically his entire thesis here was that they came up with interesting little things to describe what it was they're talking about, and just basically like they were invoking whatever they wanted to talk about rather than like spell it or anything. So one example that he gives is like they would go like this and then make a T and then go like this, and Brady quite correctly guessed that this is drink tea, and he told them that this means land when you point at the ground. So he says, what does drink tea land mean? And he's like, drink tea the England. So like these particular monks said that England, the shorthand for England, was drink tea land. So there's all sorts of weird shortcuts in their system that they got there. Anyway. So, Soul Reaver, got any questions or things you want to see? I mean, otherwise I'll go back to who's it's there. I'll go back to some Calc 2. There's also another method that I wanted to talk about tonight, which is very similar to trapezoid, whatever, the trapezoid rule, which involves a different kind of approximation, which is very similar. You got it. All right. So the other... Nice. You want to talk about it, let me know. So the other one that comes up was developed by a guy named Simpson. So Simpson's rule is another kind of weird / interesting one. Oh man, I love this song. It comes up every so often. I have I want to say a very limited playlist, whereas I have access to like 4,000 songs or something on Pretzel. I swear only like 40 actually come up. Of course, it has to be YouTube safe, so that cuts out a whole bunch. So anyway, Simpson's rule, developed by this guy, Simpson. Let me actually get his name, because, you know. Really? But you're not going to tell me who Simpson was? Insulted. All right. Really? Thomas Simpson. There we go. Took me long enough. Should have clicked on that one in the first place. So here's the thing with trapezoid. Well, okay. Riemann sums, yes, had left, right, and midpoint, because you could use any one of those to start your rectangles. And again, in terms of when you're looking at some sort of curve like this, if you start on the left, then you're going to overshoot your area if it's a decreasing function. And if you start, no, sorry. If you're still starting on the left, but you have an increasing function, then you're going to undershoot. So you just kind of have to know, like, your value is going to be approximately, too large on this side and too small on this side, which is kind of nice because if you have both in one function like this, then they end up canceling each other out somewhat. If you go with a right, then this ends up doing exactly the opposite. So you're undershooting on a decreasing function, and you're going to be overshooting on an increasing function. And then if you have, again, same function because it's totally the same. If you do a midpoint, then you've got in each rectangle, you have a little bit that overshoots and a little bit that undershoots. And so those cancel each other out nicely as well. And typically, the midpoint rule is better. You know, doing a midpoint calculation approximation is generally better on Riemann sums than either the left or the right, unless, of course, you have one that is, again, increasing and decreasing in the same interval, roughly about the same amount. If that happens, then again, those could potentially cancel each other out almost perfectly, and then happen to be closer. But most of the time, your midpoint rectangles, midpoint Riemann sums, will be better than either the left or right. In terms of the whoa. That was not supposed to happen. Okay. Apparently I left my cursor over on the other screen, but then anyway. So when you're doing, when you're doing trapezoid rules, you have no need for this left or right notation stuff, because again, one trapezoid is going to go from the left-hand side of that Riemann approximation to the right-hand side of that Riemann approximation and draw a line directly in between them. So again, your Riemann sum, right hand would be here, left hand would be here. And then we are literally just slashing across that rectangle. So if we cut directly across the rectangle, that's taking each of those rectangles that we see throughout the entire thing, the undershooting and the overshooting, and it's just chopping them in half. So it's it's counteracting what you see in this stuff, yeah. And then the other part is that the Simpsons rule. Do I want to mention Simpsons rule at that exact moment? Let's see. So the Riemann sums, again, you're chopping them in half, or you're chopping the extra bit from the right Riemann sum in half. So yeah, Simpsons rule. So Thomas Simpson said, okay, well, this Riemann sum thing is pretty good. The trapezoid rule is even better, like almost always. Because then you're going to have, again, the extra bit here is going to get chopped in half. What if, instead of doing just a linear, you know what's coming, instead of just doing a linear chop across, what would happen if we bumped it up one level in the polynomial family? There we go. Oi. And we said that within this first group here, we're going to let this function be a parabola. So instead of, again, look at something like this. We're going from A to B like that. And then again, if we're going to let delta x be whatever this size is here, again, normally what we would see, the trapezoid rule would take this and chop it as a straight line linear function. The parabolic trajectory, on the other hand, would say, like, what would happen if we had something that looked, roughly speaking, like this. So, according to my crappy drawing, it's not super great because it's kind of like the part here was almost straight to begin with. But realistically, right, if you just take any one of these curved segments and do the same thing, so, you know, you got this nice curve that goes from like here to here. Right, if this was one of our curves, or one of our segments that we had come out with, this is saying, oh, well, if we take this as a parabola, it goes like this. Then this looks way better. It's like this, this function here is going to look better in this area in order to find a better approximation. Okay. So if we let the slices be parabolic like this, this allows us to say, all right, how do we formulate this then? Well, this is going to be... That was not it. Nope. Don't you start it. Oi. Alright. That's not it either. So I didn't actually learn the parabolic part of it, which is too bad because it makes way more sense. So for each segment, you're going to approximate this as the integral from x sub I to x sub I plus 1, or x sub I minus 1 to x sub I, whatever we're doing, of p of x dx, where p is a parabola. Or you could even do this as just generally a polynomial. So I don't personally mess with any of that, but in theory, you could do a higher order Simpson's rule and do something with like a cubic or a quartic polynomial instead of just a parabola. But this gets really big really quickly, so like if you start adding terms to all this, it's gonna just keep expanding out. So then, for each of these segments, x sub I to x sub I plus 1, our f of x dx is going to be approximated by the integral of, as we go from x sub I to x sub I plus 1, of p of x dx, which is going to be equal to integral x sub I to x sub I plus 1 of ax squared plus bx plus c, which is super easy to do, right? Because now it's just a polynomial. So this is going to be a over 3 times x cubed plus b over 2 x squared plus cx evaluated from x sub I to x sub I plus 1. Oh, you know what? No, that'll be fine. Okay. So this is saying that I actually messed this up, but so yeah, basically the derivation that they want to do has to do with if you have your function like this, and we just want simple subintervals like that. Then this would be x sub I, this would be x sub I plus 1, and this would be x sub I plus 2. Technically, what you'd want to do is have P1 here and P2 here, P sub I, and P sub I plus 1 here. And then we'd be looking at the two subintervals together. So technically, this should be I plus 2. So then all this stuff taken together, and I have to do that all out now. All right. All right, so this is all going to be equal to a over 3 parentheses x sub I plus 2 minus x sub I. And those individually are cubed. Right, so each one individually, when you take their antiderivative, you're going to get a over 3 times x cubed, and then evaluating each one of them, we get the x sub I plus 2 cubed minus x sub I cubed. All right, then the next one's going to be same deal, b over 2 times the quantity x sub I plus 2 squared minus x sub I squared. Plus c, parentheses, x sub I plus 2 minus x sub I. Alright, so then... Oh, gross. Okay. What they do here is they take out an x sub I plus 2 minus x sub I from each of these things, and these are now a difference of squares rule and a difference of cubes rule. I don't remember them almost at all, so that's fun. But x sub I plus 2 minus x sub I is then multiplied by x sub I plus 2 squared plus x sub I plus 2 x sub I plus x sub I squared plus b over 2 times x sub I plus 2 minus x sub I times x sub I plus 2 plus x sub I plus c times x plus 2 I plus 2 minus x sub I. Okay, and then remove x sub I plus 2 minus x sub I, and we can divide all of these things, or factor out, I should say, a common factor between them, and that's going to be a 1/6 at the bottom. That leaves a 2a times x sub I plus 2 squared plus x sub I plus 2x sub I plus x sub I squared. Yeah. Plus, this is now going to be a 3b with x sub I plus 2 plus x sub I plus c. The x sub I plus 2 minus x sub I is gone from there, so that's... oh, right, and we got 6 of them. Because again, we factored out a 1/6, so there only being an over 1 there, that's going to take that up. Alright, then it should be noted that over here, x sub... x sub I plus 2 minus x sub I over 2 is going to be equal to delta x or delta x sub I, whatever you want to particularly write there. So this makes the entire top portion nope. Alright, so the integral, again, just from above, is going to be equal to then delta x over 3 times all this stuff again. Or then rearranging stuff. Alright, so rearranging all the things. Where'd that 2 go? Oh, split it into 2 terms. Yeah, there we go. For convenience's sake, that's how they do this. Okay, so they're going to take these 2 a times x sub I plus 2 squareds and split them into 2 groups. One is just going to be a x sub I plus 2 squared, and the other is going to be an a times x sub I plus 2 squared further on down. You'll see how it works in a sec. Jerks. And this is going to be a 2a. Nope, sorry. This one down here is going to be our 2a x sub I plus 2 x sub I. Which then also is going to absorb in the 2a. Nope, sorry, that's going to also split. So we're going to get an a. Not here. We're also going to get an a x sub I squared over here and an a x sub I squared over here. Now this, very conveniently, makes a sum of squares. Up here, these two are going to be separated into things that use a, b, and c, which then allow us to use the original formula f of x from up top. I get it now. So 3b x sub I plus 2 is going to be split into two different pieces. One is going to be here, so b x sub I plus 2, and also down here. There are now two more b xi sub 2's. The 3b x sub i's are going to be split again, one over here, and one down here. Or, sorry, two down here. 2b x sub i's down there. Alright, then the 6 c's are going to be broken up into 1 c here, 1 c here, and 4 c's down here. Yeah. I know, right? I was not expecting this. There is also another algebraic way of coming up with derivation. There we go. Which may not make as much sense. I think it kind of depends on the student. I want to show both, because if somebody doesn't get it one way, then getting it a different way would be helpful, or trying to explain it a different way would be helpful. This here is f of x sub I plus 2. This here is f of x sub I. This here is x sub I plus 2 plus x sub I squared times a plus 2b parentheses x sub I plus 2 plus x sub I. This next part's going to make it flip probably. Plus 4c. Hang on one second. All right. Yeah. My spouse was just talking Olympics. So anyway, yeah, we got this stuff. Delta x over 3 times the quantity. So then we got to look at oh, yeah. Okay. So then the other one that is we want to use here is that from above we had all this stuff here. This was x sub I. Oh no, that's delta x. We don't want that. We want that x sub 1. Nope. X sub I plus 1 is going to be equal to, or again, approximately equal to, because technically it's not necessarily going to be equal to, but it's going to be really close. And especially if your delta x is really small, it literally will be, if not equal, then very close to equal to the average between x sub I plus 2 plus x sub I. The average of x sub I plus 2 and x sub I. Which then means that twice x sub I plus 1 is going to be equal to the sum of x sub I plus 2 and x sub I. Which, oh look at that, we have that. X sub I plus 1. X sub I plus 1, that's twice x sub I plus 1. For both of these. So, f of x sub I plus 2 plus f of x sub I plus, this is going to be a times 2, nope, sorry. That 2 is going to be squared, so we get a 4a x sub I plus 1. Here, we get a 4b x sub I plus 1. And here we get a 4c. Oh, would you look at that. It's yet another f of something. So, it's delta x over 3 times f of x sub I plus 2. And if we order them in terms of their subscripts, this is going to get us a 4 f of x sub I plus 1 plus 1 f of x sub I. Like that. So if we do a large number of sub-intervals, what's going to happen is we end up with the sum of n sub-intervals ends up being delta x over 3, I know, right? Times f of x sub 0, right? We could reorder this or do it like... So that's Simpson's rule if we only have 2 subintervals, which we take them essentially in pairs. So if we do the first 2, this is what we get. If we do the next 2, then what we get, and this is a little weird, is if we do the next 2 in here, what we had was 1 of the first one, 4 of the middle one, and 1 of the second one, right? Then if we take the next 2 subintervals, so that gets us the approximation for these 2. If we take the next 2 subintervals, which are here and here, then this gets us another 1, 4, 1 pattern. Yeah, there you go. So then what does that get us in total? That's going to be a 1, 4, 2, 4, 1. And then if we break it up into smaller subintervals, it does the same thing over and over and over again. It has to be still in, like, pairs, so it still has to break down nicely to make this work. But we end up with one of the first subinterval, or one of the first function value, so f of x sub 0, plus 4 of the next one, f of x sub 1, plus 2 of f of x sub 2, plus 4 of f of x sub 3, plus etc., all the way out to, let's say, 2 of f of x sub n, n minus 2, plus 4 of f of x sub n minus 1, plus 1 of f of x sub n. So generally speaking, that's how the entire Simpsons rule works as a whole. And so we see this Simpsons rule with n subintervals for this particular function ends up working out like this. It's just alternating 2s and 4s in the middle, and then 1 at either end, for the same reason that it did for all that stuff up above. So then if we do this with sorry. If we do this with the function that we had up above, right, this one, then what we can do is say, okay, where's Octave? So we can reconnect on Octave and say that we want to do, okay, so x is going to be equal to, here's the thing. So let's do a small subinterval first. Let's do, right, 0 to 1, but taken as, let's just do the 10 that we had before, so 0.1. So y is equal to, this is going to be, again, exponential of x dot raised to second power, mute, and that gets us all the values back again. So now we just have all the values. So if we did it manually, I don't recommend this, but it's perfectly possible. Del x equals, yeah, I should have done that again, 0.1. So s is going to be equal to del x times, so this is where we get the Simpsons rule stuff. So this is going to be y of 1 plus 4 times y of 2 plus 2 of y of 3. Again, I don't recommend this. You can do it perfectly well by doing a for loop or like literally anything. Alright, I'll see you later, Solar Reaver. I'll if you come back later, you can check this one out. Yeah, so I'm going to be back on Friday with another game stream. Probably it's going to be like one of my last Risk of Rain 1, and then probably some other fun stuff. Oh, yeah, Friday is my game stream, so that's why I do that. But I've been trying to get a Monday morning math stream off the ground, and like I'm just always busy and doing stuff and making sure my kids are, you know, occupied. So I don't really, I'm not sure I have actual time for it, which is too bad. But at any rate, I hope you have a good couple of days. And I'll see you next time. Yeah, definitely send me questions. And I'll see what I can get to. Yep. And hey, if you want to come in and play for that, then you're welcome to do it. It's not like I'm, you know, I don't have affiliates, so like I'm not making any money off of this. All right, 4 times y of 10 plus 1 of y of 11. Okay, so that's del x. I need to divide everything by 3. And that comes out to be 1.4627. So now we can see that this has, only with 10 subintervals, we now have the more accurate number that we did for the trapezoid rule with 1,000. Now, granted, the trapezoid rule probably didn't actually need 1,000 to get to this level of accuracy. I might actually go back and try to find, like, you know, how close can we get it with 100? Or how close can we get it with, you know, however far it's going to be. But, yeah, so S in this particular case, the sum based on Simpson's rule is going to get us the same level of accuracy as at 10 subintervals that the trapezoid rule did at significantly more than 10. Right? So, like, I don't actually know what it's going to be. And, oh, actually, we can go back up. So, let's try this. Okay, so here's the trapezoid rule with del x being, with del x being 0.1. So then let x be all the numbers 0 to 1 by 0.01. So hundredths instead of thousandths. Let's mute, and then we'll do y being the same thing that we did before. And I keep screwing this up. Del x just being 0.01. Alright, so then let's try to figure out in 100, how's this going to do for us? Yeah, so trapezoid rule, it'll be less than 100 iterations to get that same level of accuracy. And again, I can plug in different numbers all day. But at any rate, so I think probably now is a good time to duck out for me as well. But thank you everybody for coming. Thank you Soul Reaver for showing up, and thank you everybody for watching on video on demand. I will probably be spending most of the rest of the night in Sea of Thieves because some of my friends are online, and this is what I've been doing for the last 5 days. That's why I didn't have any bonus streams. At night. Bonus streams at night. So anyway, hope you all have a good night. I will see you on Friday night for games, and we'll see what other things I have laying around, because I think I've got some. Well, I do have some other things I want to get to, but anyway. So, see you on Friday for Risk of Rain 1 and maybe some other stuff. We'll see how that goes. Have a good night, everybody. This is Obi-Wan Pez for N Simplex Pachinko, and we will send a raid over to, because I totally forgot. Let's send a raid over to Adriosa. I just found out is online again, so she's had a vacation for the last bit. So I think I'm going to send us over to her. And Jason Charles Miller's group is going to, the Miller's Chillers, is also going to be hopping into Adriosa's at some point. I know he's going to hop in. They're good friends with each other. So, anyway, hope you all have a good time. I'll see you on Friday. Good luck. Obi-Wan Pez for N Simplex Pachinko. Signing off.